All right, so let's continue with question 7, part 3. And what I've done is I've copied the equation that was given in part 1 so that I don't have to scroll, because what it's asking, it's saying that if the iterative formula converges to a root, then like this iterative formula, if this converges to a root, show that it converges to the root of the equation in part 1. And to do that, you have to basically show that the iterative formula and the equation are the same thing. They can be rearranged to give one another. That's all you need to show. If you show that, then obviously whatever root that comes out of the iterative formula, will obviously be the root of the equation, because if they're the same thing, if they're simply, the only difference between them is a bit of algebraic manipulation, a bit of simplification, then obviously the root that comes out of the iterative formula is the root of the equation. Now, there are two ways to do this. You could either simplify this to look like this, or you can simplify this to look like this, which is I'm going to do the latter because I think that's a little easier, but either way is acceptable. So to do so, what can I do? I can simply put ln on both sides, ln e power 2x. And understand here there's a positive, there's a plus sign, it's not a multiplication sign, so you can't split them. You can't write ln 6 plus ln e power minus x. You have to write the entire bracket together, because that property is only valid if there was a multiplication sign between 6 and e. Anyhow, this can go here, giving 2x, leaving ln e, which is 1, so you can just cut that. And this is ln. Let's try to do a bit of simplification, because I don't think they've given it in this value. I don't see any e power minus x, so I'll try to simplify accordingly. I can write e power minus x as 1 upon e power x, right? And you have 2x here because like the one ln e is just 1, right? So that doesn't really matter. Let's try to simplify more here. That gives me 6 e power x plus 1 upon e power x. Now this is interesting. Do we have a minus 1 here? We don't really have a minus 1 here. But what I think what I can do is I can simply write this as ln, and let's write this as, well, 6 e power x plus 1, because then I've got at least part of my thing proved, so at least have something in the bag. And now notice here the property can apply, because these two things, well, they're dividing, right? So if these two things are dividing, then I can write the numerator minus ln and the denominator. I can do that, which gives me 2x is equals to ln 6ex plus 1, which is very similar to what I want. I can simply write this as minus x. The reason being because it was ln e x, x can go here, and ln e just gets cancelled out to 1. And the minus sign was there, so I can simply write this as minus x. Whoops. Anyhow, so if it is minus x here, I can take this on the other side, and that would give 3x, because if it's minus here, it will add there. And if you kind of tidy this up, x is equals to 1 upon 3, because the 3 comes and divides here. ln 6ex plus 1, is that literally the same thing as the iterative formula? Yes, it is. And hence you basically proved that it's the same thing. It's going to converge to the same thing. It's going to converge to the same root. You're good with that. And now you have to use this iterative formula to calculate the root correct to 3 decimal places. Give the result of each iteration to 5 decimal places. So what you're basically going to do, you're going to keep putting it inside the iterative formula until you get the value of x, that is 2 values of x, two corresponding values of x that are ditto same to 5 decimal places that are just identical. That's what you're looking for. Okay, so I'll just copy this to make our lives easier. The only question, the only thing you could possibly have to use your mind here in part 4 is where to start. Now it's kind of obvious since well, you haven't really proved, yeah, you proved that the root lies between 1 and zero point 0.5. So definitely don't start with like 0.25. You'll still get there, but it'll take you ages to get there because because there's no point, right? You shouldn't start with like x is equals to 1,000 when you know the root lies between zero point 0.5 and 1. What a lot of people do, they start with either zero point 0.5 or either 1. That's also fine. But the idea here is it will take you less time and fewer iterations required if you start somewhere if you start with a value of x that is very close to the root. Now I don't know what the root is, so this is just going to be an educated guess on my bit. If it lies between zero point 0.5 and 1, I mean the best bit of me starting with a value of x that is close to the root is like 0.75, right? Just the midpoint of it. No idea where the root lies, but this is just my way of ensuring that I can minimize the amount of iterations and get there faster. Anyhow, iterations are just simple. You take this, you input it into the x value here. You get x2. The output is basically that you get is x2. You input that again, you get an output that is x3. You can input that again, and you keep going on till you get two values that are identical to 5 decimal places. So I'll just do that. I'll just skip over that. That's pretty easy stuff. Now this one was a little painful because it took a lot of iterations. In fact, I think this was the third. Was this the 12th? Was this the 13th? Anyhow, there's a lot of iterations, but the idea here is you continue till you get identical results for the level of decimal places that they're signified. Once you get those identical results, you take them and you round them off to 3 decimal places because that's what they've told us to do in the question. They said give iterations to 5 decimal places and your final answer to 3. So that's what you do. Okay, partial fractions. So you have to put fx, express it in the form in partial fractions, and we know it's not an improper fraction because, well, if you multiply the brackets in the denominator, you will get x cubed, and in the numerator the highest power is just x squared, so that's completely fine. So what we can do, we can write this as a upon 2x plus 1 plus, now this is a little different from, let's say, x plus 9 squared. That would be what we call a repeated fraction, but here it's a quadratic one. So for a quadratic one, you have bx plus c upon x squared plus 9. That's what that's what the idea here is. So what you then do, you take your LCM, and once you take your LCM, your denominators cancel out. I'm not going to go in the details of that. I'm just going to skip directly to what we need to show on the paper, which is this. And once you took your LCM, you get something of this form. Your a multiplies with x squared plus 9 plus bx plus c multiplies with 2x plus 1. And if you want to, you can just further simplify that. You can simplify this down to, well, not that much, but you could write 2x plus 1 with bx plus c 2x plus 1, rather than just keeping these two as separate brackets. Okay, so partials are kind of boring, so I'm just going to skip ahead on these, and if you want, you can just follow the working that I did. So here's the working in case someone wants to look at it. The only thing to note here is to take values of x that kind of cancel out stuff like the convenient values. Like if you take x is minus 1 upon 2, that makes b and c 0. So you can isolate a and solve for that. If you take x is 0, that makes b 0. So you can and you know a, so you can isolate c and solve for that. And then you just take a convenient value. I took x is equal to 1 so that I don't have to do a lot of calculation. Just put that in and get b. So if anyone wants to pause and actually go through the steps, more than welcome. But I thought they were simple enough to skip. The well, one thing to take note of, and something that a lot of people do, a common, basically something a lot of people do, basically a common mistake, is to just figure out A, B, and C and stop there. That was not what the question was. The question was to express f of x in partial fractions, and hence you have to pop it back into the original expression that you came up over here. Right, that was this. You have to come back to this, and you have to put in your values of A, B, and C. That's required, and a lot of people just forget to do that. Anyhow, you have to then integrate this expression and give your form in ln c, where c is an integer. Okay, I just copied this, equation down so that I just don't have to keep on scrolling up and down. So an easy way to think of this is, well, I believe in both of the integrals. One thing that you have to remember is how if you have a function in the denominator and you have its inverse, it's differential in the numerator, you can simply write this as the ln of that particular function. So like, if you have 1 upon x, the differential of x is 1, so you can simply write this as, let's say, ln x. You need to remember that. So first, let's split this up. That'll make our lives easier. I can take 3 common, 1 upon 2x plus 1 plus x. You can't take variables common. I hope everyone's aware of that. Like if it was 2x, I could take 2 outside. Again, I've taken 3 common for the specific the specific fraction. But yeah, if I had 3x, I could only take the 3 part common. I can't take x common. It's obviously to the same limits. Okay, so what is the differential of 2x plus 1? That's 2, right? Plus 1 that has no, plus 1 would just be 0 and 2x would be 2. So what you want here is you want a 2 here. Then you can use that property. But you can't simply add it just because you want to. You have to ensure that it has no overall effect on the equation. And to do so, you can simply divide a 2 outside, because you can simply cancel these 2 2s and it would be the same thing before you had started meddling with it. But since you put it like that, now since the expression you have in the denominator, its differential is there in the numerator, you can write this as 3 upon 2 ln whatever was there in the denominator. You've successfully integrated that. Okay, what's the integral of 2x plus 9? What's the differential of 2x plus 9? It is 2x. To do so, you need 2 here. You already have x, but you need 2 here. And you can do that by basically multiplying this by 1 upon 2, so that the 2's could theoretically cancel. That gives you 1 upon 2 ln x square plus 9. Right? And I can make this more simple by simply taking whatever we have as multiples, right up there with the expression using the property of log. I can take whatever's multiplying with the ln and put it there as the power in the bracket. Now, if 2 logarithms are adding, their internal brackets could simply multiply. We've learned that. But the internal brackets, not the ln, just the internal bracket. So x squared plus 9. And the reason I'm doing so is because now it becomes much easier for me to apply limits. I had to apply limits to this For what? For 0 to 4. Becomes much easier. Now I put in ln. Uh, let's just use better bracket. I put in ln 4. What's 4? 2 into 4 is 8. 8 plus 1 is 9. That is 9 c upon 2 into 4 square is 36. 36 plus 9, I believe, is 45. So you want root of 45, right? Yeah. Okay, so you have this. This is your upper limit. You have to subtract this with your lower limit. This is ln. Now you just put in your zeros. So this is basically 1 raised to the power 3 upon 2 into 9 minus 9 1 upon 2 is basically 3. It's going to be 3. But I'll still write it. Yeah, you got that. So it's your upper limit minus your lower limit. And let me just, well, in fact, I think we have to give this in a form of c, where c is an integer. So let me just use my calculator to help me a little. Yeah, and on a side note, I'm an idiot. 4 squares of 36, 4 squares 16. So like 4 square plus 9 would be 25. This would be root of 25, not root of 45, which makes life much more easier. Yeah, it happens. Anyway, so let's try to simplify, because we do want an exact, but we do have to give it in the form of ln, so we can't simply pop everything into our calculator. So this is ln. What is 9 raised to the power 1.5? Well, if you think about it, 9 raised to the power half would be 3, and 3, well, and 3 cubed would be 27. Or you could just be a sane person and use your calculator. And 25 root is 5 minus ln. This is simply going to be 1 raised to whatever is still going to be 1. And 9 raised to the power 1 upon 2. 1 upon 2 is basically like a root. So it's 3. That's fine. Okay, so you have ln. You have 27 into 5, which is 135. You have minus ln, and you have 3. Now, if two logarithms are subtracting, you can simply write it like this. And if you want to simplify, 135 divided by 3 is 45. This gives you ln 45, which is good, because it satisfies the requirement of the question. They wanted it in the form of ln c.